In this problem, we're given the voltage across a 5 microfarad capacitor. We're asked to find the waveform for the current, and also we're asked to calculate how much energy stored in the capacitor. T is equal to 4 milliseconds. Given the voltage and asked to find the current, remember our relationship for our capacitor, I is equal to C dV dt. So we'll be using that expression. Now we need to go through and find expressions for the waveform over different intervals. Then we'll be able to apply this expression to those waveforms to calculate the current. So let's start off with this first interval between 0 and 1 millisecond. Straight line. Remember the equation for a straight line is y is equal to mx plus b. B is the y-intercept. Here it's easy to see that B is 0. Our slope here is 5 volts over 1 millisecond, and that's 5,000. So then the voltage in this interval is 5,000 T volts. Now, let's do the next interval from 1 to 3. It's fairly easy. We can look and see the voltage is constant. So over this interval, V of T is just 5 volts. So that's easy. The slope is 0. Now let's look at the next interval, which is 3 to 4. And if we look at our waveform here, the voltage is going to go from 5 to 10 over a millisecond. So our slope is 10 minus 5. We got 4 milliseconds minus 3 milliseconds to give us a slope of 5,000. Now we need to calculate the y-intercept, so we know that V of T is 5,000 T plus B. And if we look at our waveform, we note that at T equals 4 milliseconds, the voltage is 10. So V of T equal 4 milliseconds is equal to 10. That's 5,000 times 4 times 10 to the minus 3 plus B. That tells us that the y-intercept is minus 10. So over this interval, the voltage V of T is 5,000 T minus 10 volts. Now for our next interval, from 4 to 7, you have a straight line. We're going from 10 to minus 5 over 3 milliseconds. So our slope now is minus 5 minus 10 over 7 milliseconds minus 3 milliseconds. That's a slope of minus 5,000. So now we need to find the y-intercept. So our equation is minus 5,000 T plus B. And if we look here, the voltage waveform goes through 0 at T equals 6 milliseconds. So V of T equals 6 milliseconds is 0, and that's minus 5,000 times 6 milliseconds plus B. And if you solve, you're going to get B is equal to 30. So now our waveform over this interval is minus 5,000 T plus 30 volts. And now we've got really 3 more intervals. 7 to 9 is pretty easy, and T greater than 10 is easy. So between 7 and 9 milliseconds. V of t is minus 5. Okay, now between 9 and 10, now we're going to go from minus 5 up to 10. So our slope now is 0 minus a minus 5 over 10 milliseconds minus 9 milliseconds is 5,000 again. So we have V of t is 5,000 t plus b. And if we look at 10 milliseconds, the voltage is 0. This gives us B is equal to minus 50. So then our expression is 5,000 t minus 50 volts. And for completeness, we'll just say for t greater than 10 milliseconds, okay, V of t is equal to 0. So now we've found description. Let's summarize. So we have V of t then is 5,000 t volts (5 volts). Then it's 5,000 t minus 10 volts minus 5,000 t plus 30 volts minus 5 volts minus 5,000 t minus 50 for 9 to 10 milliseconds, and then 0 for t greater than 10 milliseconds. So there's the description of our voltage waveform. Now we're ready to use I is equal to C dV dt. Okay, so for our first interval, for instance, for 0 to 1, we have I of t, 5 times 10 to the minus 6 times the derivative of 5,000 t. That gives us 5 times 10 to the minus 6 times 5,000. It's 25 milliamps. So there's that interval. Now that next interval is pretty easy, because if we look, the voltage is constant. So in the next interval we'd have 5 times 10 to the minus 6 times the derivative of the constant, which is 0. Then that next interval, we have that, and of course the derivative of the constant 0, so we get 5,000 out of this. So we get 25 milliamps. The next interval, we have that. So we have 5 times 10 to the minus 6 times minus 5,000. So now it's minus 25 milliamps. The next interval, if you remember, from 7 to 9, the voltage is again constant. Then in the next interval, we would take the derivative of 5,000 t minus 50. And then, of course, I of t is 0 for t greater than 10 milliseconds. So now, let's sketch that current waveform. I of t in milliamps, time in milliseconds. So we're basically going to go between 25 milliamps minus 25 milliamps. So there's 1, 3, 4, 7, 9, and 10. So here's our waveform, 25 milliamps from 0 to 1, and it's 0 from 1 to 3. Then it goes up to 25 from 3 to 4. From 4 to 7, it's down at minus 25. Then it's 0 from 7 to 9. Then it goes back up to plus 25 for 9 to 10. And then we got one last calculation, and that is the energy. We have to calculate the energy at t equal 4 milliseconds. If we note, remember the energy, 1/2 CV squared. So we have 1/2, 5 times 10 to the minus 6. And if we look at the voltage at 4 milliseconds is 10. So we have 10 squared. So the energy then is 250 microjoules. So we use 1/2 CV squared for that calculation.